Okay, so in the introduction, let me introduce you to the concept of equivalent circuit. Okay, equivalent circuit. The meaning of equivalent circuit is already been introduced when we were studying about the diode, right? We had diode equivalent circuits. Now, what do you mean by equivalent circuit? So equivalent circuit, basically simulates the behavior of the actual circuit. Equivalent circuit basically simulates, or it gives the exact behavior of the actual circuit. Okay, so in equivalent circuit, what we do is we replace the device symbol. We replace the device symbol. Say, for example, since we are dealing with transistors, so what we are going to do over here is that we are going to replace the transistor symbol with some, circuit elements wisely chosen. Okay, so we'll be replacing the device symbol with the wisely chosen circuit element. So the connection of these elements basically mimics the exact working of the device. So this is what is known as equivalent circuit. All right, next. Now here we are predominantly assessing the low frequency performance. Okay, low frequency performance. Okay, but strictly speaking, your amplifiers are subjected to 3 frequencies. Okay, low frequency, then mid frequency, and then you have the high frequencies. Okay, low frequency, normally the range will be in hertz. Range is in hertz. Okay, on the other hand, mid frequency, we say from few kilohertz to several hundreds of kilohertz. So that's your mid frequency range, and your high frequency going to be anything greater than megahertz. So this is the widely accepted the frequency classification. All right, now if a model is developed for low frequency, okay, it can also be used for mid frequency as well as high frequency. Okay, so the low frequency model can be directly used for mid frequency frequency range also. On the other hand, in high frequency, what we do is we slightly tweak the model which was proposed for low frequency. Okay, so for high frequency, what we do, we modify the low frequency model. Low frequency model. Let's see how exactly we modify the low frequency model in order to suit the requirements of high frequencies. All right, fine then. Okay, so that's about the equivalent circuit and something known as the frequency spectrum. All right. Okay. Now, as I was mentioning in the previously, that there are majorly 3 models. Okay, the first model is the RE model. Okay, over here itself I'll tell you why it is called as RE model. So this RE model is basically derived from diode resistance. Okay, in case of diode circuit, the AC resistance or the effective resistance small re can be given as 26 millivolt divided by the DC emitter current IE. Okay, so on the input side, the P and N layer. Okay, so P and layer is basically your diode layer, right? Diode is a PN junction semiconductor device. So even in transistor, okay, even in transistor, let's say for example, I consider NPN transistor. This is base, emitter, and collector. Okay, so I'm considering NPN transistor. So let me write on the terminals. N terminal. So base going to be the P terminal, and emitter going to be the again N terminal. So there are two N terminals and one P terminal. Now, if you look at the input circuit, what do you observe? If you look at the input circuit, okay, you observe that, okay, or you see that there are two layers coming into the input circuit, right? What are those two layers? A P layer and a N layer. So this PN junction basically, talks about the diode layer. So you can say that there is kind of inbuilt diode effect inside a transistor. Okay, and that diode layer basically gives the effective resistance RE, and the model based on this effective resistance RE is called as RE model. So that's the meaning of RE model. Okay. Now the second model, okay, is the H model. Second model is the H model. H stands for hybrid. H stands for hybrid. Okay. Now, why hybrid? Okay. Why hybrid is due to the fact that your H model parameters, okay, H model parameters are calculated using voltage and current ratios. Okay, so you may have some H parameter, let's say Hx. Okay, don't worry about what is Hx. Maybe calculated by taking the VI ratio. Okay, so the unit becomes ohms. Then you may have some Hy parameter that can be found by taking out, say, I by V ratio. That becomes Siemens. And you can also have, some H parameter wherein we take only the voltage ratio. Let's say input voltage to, say, output voltage. So again, this becomes dimensionless because you are dividing the two voltages, hence you get dimensionless entity. Then you can also have some, say, Hx as some current ratio, output current to input current. So again, this becomes the dimensionless quantity. So basically in your H model, you observe different types of parameters. Some may have units, some may not have units. Some are derived by, taking out the voltage to current ratio. Some are derived by taking current to voltage ratio. So what is happening is here you are getting, wide variety of signal variables. There are some voltage signals, there are some current signals. So since there is a mixture of different, voltage and current signals, the parameters, derived on the basis of those signals are called as hybrid parameter. What do you mean by hybrid? Hybrid is a mix of different things. So basically, these parameters are mixture of different signal ratios. Okay, so that's the meaning of hybrid model. Okay, and then finally we have something known as hybrid pi model. Hybrid pi model. As I was mentioning, this hybrid pi model is used for low frequency analysis as well as high frequency analysis. So how to develop this hybrid parameter? You don't have to worry, very simple, because this hybrid pi model, it will be derived from your conventional hybrid model or H model. Okay, in sequence, let us study about hybrid model. Okay, all right. So that being the brief introduction of module 2. Okay. So in module 2, outcome would be, course outcome would be something like student will be able to find performance parameters of various amplifier circuit. Okay, so you will be able to find performance parameters of various amplifier circuits, and by looking at those performance parameters, you can also judge which amplifier is good or which amplifier is used for what purpose, etc., etc. You can infer from this particular course outcome. Okay, all right. Okay, any questions you want to ask? Any doubts so far? This is just the introduction, so I don't think so you should be having some doubts here. Okay. Nevertheless, if you have any doubts, just let me know. No doubts? Can I get into the syllabus?
Yes, sir.
Yeah, all right. Fine. Fine. So first let us, go for the very first model, that is ReModel. ReModel. Okay. Now, ReModel can be developed for 3 different configurations. As we have already studied in module 1, that a transistor can be configured in common emitter mode, or it can be configured in common base mode, or you can also configure a transistor in common collector mode. Okay, so depending on the configuration, you can develop ReModel for common emitter mode or common base mode or common collector mode. Okay, now in our course, we will be developing the ReModel for common emitter and common base only. Okay, we will not be developing any ReModel for common collector mode. That's because you can use the common emitter model for common collector operation also, because the output current being very close to each other for common emitter mode as well as common collector mode. Okay, because in common emitter mode, output current I0 is IC. On the other hand, in common collector mode, output current I0 is IE. Since IC and IE are comparable to each other, so the common emitter model can be used for common collector model as well. All right, fine. So let's look at the first model then. Okay, you can write the subheading as ReModel for say common emitter configuration. Okay, you don't have to break your head too much. Let me teach you in a very simple way. Okay, so step 1, what you have to do is draw the device symbol. Okay, step 1 is to draw the device symbol for common emitter configuration. Okay, so for common emitter configuration, let me draw the device symbol. Okay, so over here I am choosing NPN transistor, this being base, emitter and collector terminal. Okay, and then you mark the currents, emitter current, the base current and the collector current, such that emitter current IE is summation of the 2 transistor currents. Okay, so emitter terminal is common for input circuit as well as output circuit. Okay, once you draw the device symbol for the given configuration, you can go to step 2. So in step 2, what you can do is you can rewrite the device symbol. Okay, rewrite the device symbol. Okay, and after rewriting the device symbol, you mark the layers: N layer, P layer, and the second N layer. So it is NPN transistor, right? Now, let us look at the input circle. And let us also look at the output circuit. Okay. Let us collect few signals, as in the output current IC. Okay. And let us also collect some signals on the input side, such as the base current, say IB. Okay. Base current IB. Now, since I am considering AC analysis, okay, one important point what you have to note is that I am representing the currents as IB, IC, and IA. Okay, so this should have been small IE. Okay, IB, IC, and IA. So they represent, these currents represent RMS values. RMS values of instantaneous current, IB, IC, and IE respectively. Okay, so this is how I separate the DC analysis from the AC analysis, by introducing the RMS values of AC current. Okay, this step is very important. Okay, so do not end up in writing the DC current. Okay, all right. Now, on the input side, what do you have? You have P and N layer. Okay. Okay. So you have PN layer. Okay. So let me write on the input side. On the input side, the PN layer can be replaced by a diode. Okay, with an effective resistance, of RE ohms. Okay, so I have the standard formula for diode resistance RE. So diode resistance RE is 26 millivolt divided by IE. Remember, this IE is DC current. DC current, in bracket you can write biasing current, because biasing is DC operation. So that is how you get the value of RE. So what you have to do in your equivalent circuit is that, okay, what I will do, this is your base layer. Okay, and this is your emitter layer. Okay, I'm not marking collector terminal. That's because I want you to show how am I going to replace the base terminal, base and emitter terminal, with the equivalent circuit. So what I will do, I will replace the transistor symbol, okay, which is found between base and emitter, with a resistance RE. With a resistance RE. That is how I basically, construct the equivalent circuit for the input circuit. So this is your base terminal, and this is your emitter terminal. Okay, and through base to the base terminal, which current flows? IV flows, right? IV flows. And let us also consider the input impedance as seen from the input terminal. Okay, let's define it as ZI. Okay, now the voltage, okay, the voltage measured across RE, okay, RE, let's take it as VI, okay, VI. And let us try to write down an equation for VI as well. Okay, we will try to write an equation for VI as well. Okay, fine. So that's about your input circuit. Okay. Next, let us talk about the output circuit. Output circuit. Okay. Now, in the output circuit, okay, we have output current I naught as IC. Okay. Now, this IC can be given as beta times IB. Okay. So on the output side, we have a flow of output current, okay, which can be given as beta times IB. So IC is equal to beta times IB, right? We are writing the equation as, what is beta? Beta is a gain, current gain, dimensionless entity. So IC can be represented as a controlled current source. Okay, so IC can be represented as a controlled current source. We say in network analysis something like current controlled source, right? So value of IC is controlled by IB by a factor of beta. So on the output side, C and E terminals can be, replaced with a controlled source. Okay, let's see, how exactly the output circuit looks like. Okay. So base I'm not going to show here. So this is your collector and this is your emitter. So what I'm trying to show you is that the collector and emitter terminals now can be represented with something like a controlled source. Okay, controlled source. So this is IC, which is beta times IB. So this being your collector terminal and this being your emitter terminal. Okay, now, so far what we have done is we have introduced some equivalent circuit on the input side and some equivalent circuit on the output side. Okay, now what we have to do is we have to connect these two circuits together so that it represents the complete equivalent circuit of your transistor. Okay, so let's do it in step number 3. Okay, so let us collate everything in step number 3. Okay, so this is base, collector, and emitter. Okay, so this can be represented something like this, as I have already told you. Okay, this is base and emitter. So between base and emitter, you can place a diode, right? And this is what the collector terminal looks like. And through the collector terminal, current IC flows. IC can be given as beta times IB, correct? And through the base terminal, base current IB flows, and through the emitter terminal, emitter current IE flows, right? And also we had seen that the diode, PN junction diode, okay, this is your P layer and this is your N layer. So P and N layer can be replaced with a resistance RE, right? The resistance RE. So this is your circuit A, this is your circuit B, okay? And IC is equal to beta times IB can be replaced with a controlled current source. Okay, arrow direction is downward because IC current direction is downwards. So this is IC, which is equal to beta times IB, right? Fine. So now let us, join the two circuits in a more meaningful manner. So what I will do, I will consider the input terminals. Okay, input terminals are base and emitter. And let me also consider the output terminals. What are output terminals for common emitter configuration? It is collector and emitter. Okay. Now, in between, the input port and output port, you are supposed to place, what do you say, the elements, right? So between base and emitter, we have what? Resistance RE. And between collector and emitter, we have a controlled source IC, which is given as beta times IB. Okay, and then you can join the two because the emitter is common terminal to both input circuit as well as the output circuit, right? Output circuit. Okay. Now, yeah, I just want to tell you one thing that, okay, what I will do here is that let me consider this as ZI. Okay, I'll tell you why also. Now, this is your base current, right? This is your base current IB. Now, when you place the circuit in this manner, what happens? The same current IB flows through this impedance ZI, right? On the other hand, in circuit number, in circuit B, if you observe closely, IB is from base terminal to this point, right? And through resistance RE, okay, through resistance RE, which current flows? Current IE flows, right? So what we will do is we will try to find out the impedance ZI here. Okay, so let me write here. Okay, from circuit B, input impedance ZI, okay, can be found as VI by II. Okay, so what is VI? So VI is nothing but the voltage measured across the input terminal. So what are the input terminals? Base and emitter. So this is your VI. This is your VI. Okay, you can follow, right? This is your base point and this is your emitter point. Across base and emitter, whatever you measure, that will be your input voltage. Okay, so that's your VI. Now, VI is what basically? Voltage is equal to current into resistance. So through RE, which current flows? IE flows. So you can write VI as IE into RE divided by II. What is II? II is your input current IB. Okay. Now, approximately what we can write is IE as IC. Okay, and RE. And this is IB. Okay, that's because IE is approximately equal to IC. Now, what is this ratio? IC by IB. So IC by IB ratio is beta. Okay, so in case of common emitter configuration, the input impedance appears as beta times RE. Okay, so it is not RE, it is basically beta times RE. That's because the current gain amplifies the input impedance. Okay, so this ZI now can be replaced with beta RE, and this can be considered as the same base current which gets into ZI as well. Okay, so this is your equivalent circuit. Okay, now in your equivalent circuit, sometimes, we also introduce the output impedance, output impedance. This is R naught. Okay. So R naught is equal to output impedance. So for a common emitter configuration, this output impedance will be in, in tens of kilo ohms. Okay. And the input impedance, okay, will be in few kilo ohms. So that's the normal range of input and output impedance for a common emitter configuration. Okay, common emitter configuration. Okay, now let me write down the final circuit, a neat final RE model. So let me give the heading as RE model of CE config. Okay. This, let me take it as beta RE. This, let me consider it as IC, which is equal to beta IB. So this is my IB. Okay. And let us also mark the output resistance R naught, or output impedance. Okay, and this is going to be your output port, collector and emitter, and this going to be your input port, base and emitter. This is where the input is applied, and this is where the output is observed. Okay, so base is at higher potential compared to emitter. Similarly, on the output side, collector will be at higher potential compared to the emitter. So this is your final circuit. Okay, and you can also mark the standard current directions. So as per two-port network topology, we assume inward current directions. So I naught, and over here we would take the inward current direction II. Okay, this is how we take the current directions. Okay, all right. So this is about your RE model of common emitter configuration. Okay, so next up we have RE model of common base configuration. Okay, this is very simple, much simpler than common emitter configuration. Okay, in the previous case, I had considered NPN transistor. Now let me consider PNP transistor. Okay, doesn't matter. You can even choose the NPN transistor. The model remains the same except for the current direction inversion. That's all. Okay, so let us choose PNP transistor. Okay, because we never considered PNP, hence let us consider at least one PNP transistor. Okay. So step one, as I have told you previously, you have to draw the current direction. Okay, so in case of PNP, the current direction is inward. Okay. So this is your emitter. Common base. So base terminal is common to input circuit as well as the output circuit. Okay, and this is your collector and this is your base. Okay, next you mark the current directions. Emitter current IE. Okay, base current IB. And collector current IC. Okay, collector current IC. the idea remains the same. Okay, let us also mark the layers here. This is your P layer, the middle layer going to be the N layer, and the collector going to be your second P layer. So it is PNP transistor, right? Now let us observe what do you have on the input side. So once again, on the input side, let me shade the region. You have a PN junction, right? So on the input side, you have PN junction. Okay, when you have a PN junction, what you can do is you can just replace the PN junction with diode resistance. RE. Okay, once again, RE is given as 26 millivolt divided by IA. This is the standard expression. Okay, you don't have to derive. It is, it can be easily fetched from the literature. Okay, that's on the input side, right? So this is your input side. Okay, output side, as usual, it's a current control device. So we are going to pay our attention towards the output current. So output current I0 is IC, and IC can be given as gain times the input current, that is alpha times IE. So on the output side, basically what you can do is you can just draw a controlled current source. Okay, controlled current source. Now, if you look at the current direction, you can clearly observe that current is going outwards, hence you have to put the arrow direction in this manner. Okay, for PNP, it is upward. If you consider NPN, you'll be surprised to see that the arrow direction will be reversed. Okay, you can try out, doesn't matter. Fine. So IC, let me write, IC is equal to alpha times IE. Okay, fine. So what do I have? I have input resistance, RE, on the input side, and I have a controlled source, IC is equal to alpha times IE. Okay. Now, why alpha? Because it is common base configuration. In common base configuration, the current gain is alpha. In common emitter configuration, the current gain is beta. And for common collector, the current gain going to be alpha. All right, fine. So let us, join the two circuits. Okay. Directly, I can do it. This is your emitter terminal. This is your base terminal. Okay. And on the output side, you have collector terminal and you have the base terminal. Okay. So between over here, it is very simple. Between emitter and base, you have a diode, right? You have a diode. Okay. P layer and N layer. So P is anode, N is cathode. You have a diode. Okay. And the input current going to be the emitter current. Okay. And on the output side, you have a controlled source. Okay. Controlled source, which is given as IC is equal to alpha times IE. Okay. Alpha times IE. So you have a diode, hence this diode, can be replaced with resistance RE. This diode can be replaced with resistance RE. Okay. Now over here, what you have to do is you have to once again check ZI. Okay, ZI. In this case, what happens is that ZI, okay, is VI by II. Okay, VI by II. So VI is current into resistance. So this is II into resistance. Okay, divided by II. Okay, but in your common base configuration, if you observe closely, your input current, okay, is emitter current, and the same emitter current flows through the diode as well, because it basically follows, emitter to base junction diode resistance. So basically, II gets cancelled and your Zi becomes Re. Okay, so normal range for Re is few ohms. That's the reason your common base configuration offers very low input impedance, On the other hand, your common emitter configuration had input impedance is equal to beta times Re. Okay, so beta value is generally 100, 200, etc. So the input impedance used to get scaled up for common emitter configuration. Okay, so let me write down the final circuit now. Simply you can write Re here. Okay, this is emitter and base. And on the output side, you can just draw the controlled current source with IC is equal to alpha times IE. Okay. And you can also draw R0. Okay, you can also draw R0. This is collector and base terminal. Okay. So I have already told you Re range will be in few kilo ohms and R0 range will be in few mega ohms. Okay, so this is very high. This is very high and this is very low. So this is the characteristic of a common base configuration. Okay, why very high? Because C and B, both layers will act like almost a perfect insulator. So in case of insulator, resistance is very high, and over here the resistance becomes resistance is usually found in the range of mega ohms, because that base layer is lightly doped. That's the reason the conductivity is very poor in base, and due to that fact, the output junction will have a very high resistance. On the other hand, if you look at your common emitter configuration, okay, what do you have the output terminals as? Collector and emitter. So collector and emitter both are heavily doped. Heavily doped means conductivity is very, very good. That means to say resistance will be very small, right? So that's the reason the output impedance of common emitter configuration will be in few kilo ohms or tens of kilo ohms. On the other hand, common base configuration will have an output impedance in the range of mega ohms. So that concludes your RE model. Okay. Now, yeah.